The Compton effect is another example of seeing a particle behavior for light. So another phenomenon where light behaves like a particle. All right, so what I'm going to do for the Compton effect is first describe the apparatus, and then after I describe the sort of physical setup or physical system, I will describe the effect that this person, Arthur Compton, back in 1923, it's the effect that Compton was able to observe really carefully and make very careful measurements. So I'll describe what he measured. And then after we describe what he measured, so we'll start with apparatus, we'll talk about the effect, which is the same as talking about data, right? And then after that, I will compare, or at least describe a little bit of how the wave model would make a prediction. You'll see that the prediction it makes no sense at all. And then after that, I'll show you how the particle model comes in and saves the day and is the successful model. So it turns out the wave model is unsuccessful, and the particle model is very successful. And really quickly, before your attention wands around, the reason that we know that the particle model is very successful is because Compton made very precise measurements. Right? This is data with not a lot of slop. So it clearly picks the particle model over the wave model. Okay, so first the apparatus. So we have some sort of source of X-rays. And with this source of X-rays, right, so X-rays are a particularly high frequency version of light. So very energetic light. These are what you use to in an X-ray machine to see bones. Like it skips the skin and the muscles and the tendons and goes and gets only blocked by the density of bones, right? So you use them to see through skin and muscle and tendons and blood, right? It sees through all the water. But anyway, so you have this source of X-rays. So Compton had a way to, in all of the X-rays coming out of this source, he could pick a sharply defined value of frequency or wavelength. I'm going to talk in terms of wavelength here. So secretly, you're constantly keeping track that in the vacuum, you have the speed of light, 3 times 10 to the 8th meters per second. The wavelength and the frequency of the light, they come together. In some sense, if you know the wavelength, you also know the frequency. You can always just calculate against the speed of light. But anyways, for Compton effect, we're going to talk in terms of lambda, the wavelength. So he could pick out a very, very narrow band of wavelength. So in his sample of light that's coming out after he sort of like filtered, so when he used whatever filter mechanisms he used, he could have a very, very sharply defined particular wavelength. And that wavelength, in a sense, so the reason it's mentioned as sharp is you might say that the intensity as a function of wavelength is really bright around a very particular wavelength. So that's the sharply defined. It's sharp in that it's not very wide. Here's a less sharply defined intensity of wavelength. So we're talking about the intensity of the light coming out of whatever filter that Compton might have used. Here is a situation where you have a central sort of bright, right? Brightness is intensity. You have a sort of bright wavelength, but it's not very narrow. It's not very sharply defined. But Compton managed to build an apparatus where he could use a filter, right, to only have basically a single wavelength with a little tiny bit of slop around it. So this is, yeah, very sharply defined. Right, it's a selector. The apparatus selected a particular wavelength. But anyway, so you've got this wavelength, and what Compton does is he aims this sharply defined X-ray wavelength at some graphite, like in a pencil. So here's a big sloppy collection of graphite material. And what comes away from the graphite is actually a bunch of light. So light comes off in every direction, actually, in all these directions. Even some back scattering. So light's coming off in every direction. And what Compton does is he just looks around all of the directions. So the direction straight forward is sort of defined as angle 0, and the direction, say, downwards is defined at angle 90 degrees, and midway along, of course, is the scattering angle 45 degrees, and you could even look backwards, so at back scattering. So in the backwards direction, the angle would be, say, 135 degrees if you're, beyond the 90 and halfway to 270. Wait, is it? No, 180, excuse me. Halfway to 180. Between 90 and 180 is 135. But anyways, these are the scattering angles. And so what Arthur Compton did was he took a piece of sort of another filter or another piece of apparatus, and he could look. So I'm going to draw Arthur Compton's eyeball. So here's Arthur Compton's eyeball, and he could inspect the light coming from each of these directions all the way around towards the scattering, or the original source of X-rays. So we'll say that these are the incoming light, or X-rays, and these are the outgoing or scattered X-rays. So this is the apparatus, and the apparatus, you can use the apparatus to measure data, and the data is being collected by this eyeball, and this eyeball can be placed at any of these angles. So you can imagine it's like a little telescope, and you can move it around and look at the light that comes from the scattering. So the light's not coming from any other issue other than being scattered by the graphite. So that is the apparatus. So this is the apparatus here. Okay, so when you look at the data is kind of interesting. So if you think about the data maybe is kind of simple to describe in like a qualitative way. At any scattering angle, there are all, well, I'm going to put all wavelengths, lambda. That is, you might have a very sharply defined lambda coming in, but what comes out at any of these angles from 0 to 180 degrees, and also like this would be like the symmetric other side, so you expect to see the same data on this side as you do on this side, and really it's got a rotational symmetry, like a cylinder symmetry about this central axis. But anyways, if you look off in all of these other scattering directions and you look at the light that comes after passing through the graphite, what you notice is actually this is full of all the wavelengths. But this is the big piece of qualitative information about the data. There is always a single lambda that is overwhelmingly the brightest. And and this is kind of maybe this is not quite the best way, or maybe it's not actually 100% correct to say it this way, but I'm going to say it this way because I think it sort of is about the Compton scattering effect. So I'm going to just stick with this language right now. So there is always a single particular wavelength over here that's actually a lambda prime. It is different than the incoming lambda, that is overwhelmingly the brightest. And let me show you what some example data looks like. So this lambda prime actually is always bigger than the original incoming X-ray lambda. The outgoing lambda prime, you will discover that of all of the wavelengths, all the colors of light coming towards the observer, there is a particular wavelength that is different from the incoming wavelength. It's actually longer than the incoming wavelength, which means it's less frequency, right? If you have a big wavelength, you have to have a small frequency to multiply to get the same value, speed of light. But anyway, so there is always a brightest lambda prime that's bigger than lambda, and there's only one. There's one. There's not multiple that are similar brightnesses. Okay, so so let me show you some more about the data. So for angle phi, right? So these are different angles at which to observe the outgoing light or the scattered light. For different scattering angles, there is a brightest lambda prime that I might label with the angle. That is, at different angles, there are different wavelengths that are the brightest. So let's say if you're checking scattering angle 45 degrees, so you're checking as drawn in the picture, there is a particular lambda. So I'm going to choose intensity, and this is lambda prime. As you check at different wavelengths, there is a particular wavelength that is really, really bright, like this. So this is the lambda prime at 45 degrees. If you compare this lambda prime to the original lambda, right, lambda prime is bigger, it's up the axis compared to lambda, right? So that's where lambda is. But if you check at a different angle, for example at 135 degrees, you get a really different answer on where lambda prime is. It's further over. So here's lambda prime, which represents the brightest, and it's the brightest at 135 degrees, and that lambda prime is way over here compared to the original incoming lambda is still over here, like this. So as you check at different angles, the brightest wavelength slides over, right? There aren't any other peaks that were observable, right? So at different angles, there is a different brightest wavelength. That is, different colors are bright at different angles. Okay, so this is what the data looks like, and you can go and look up lots of data for this, like lots of different angles. I only showed you 2 different angles. But it's a smooth transition as you imagine taking data smoothly at different angles. What you see is this peak smoothly slide over. And the question is lambda prime, the brightest lambda for a given angle, right? We want to know, what does this function look like, right? You can take data and the function's going to have a certain shape. But can we use a model of light interacting with charged particles in the graphite, right, where this model predicts lambda prime as an angle, as a function of the angle phi, of the scattering angle, right? And we have two models to start from. We can try the wave model, which I indicated early on is unsuccessful, and we can try an alternate model based on particles, right? Particles of light versus waves of light. So these are electromagnetic waves, right? Turns out that this is not successful, but this one is very successful. So you might say that it exhibits light behaving absolutely as a particle and not at all like a wave. So really quickly, I can do this in one line. What is the wave model prediction? Well, the wave model, if you have a sharply defined X-ray, that means you have a very sharply defined incoming frequency, right? So the frequency of the incoming light is very sharply defined. So here it is, right? Here is the incoming wave. It's only of a particular wavelength because I have a very sharply defined frequency. So, but when this incoming wave comes into the graphite material, let's think about what it does to an electron that belongs to the graphite. Because this wave is an X-ray wave, it's a pretty high energy wave. It's going to see, in a sense, it's going to see the small detail of graphite. And the small sort of atomistic detail of the graphite at the X-ray wavelength is individual electrons. So this thing comes up. Since this is a charge and this is an electromagnetic wave, this little charge oscillates up and down. And the oscillation frequency matches the incoming frequency of this, right? So if it oscillates at the incoming frequency, then I know that an accelerated charge, right? If you have oscillation, that means you are accelerating, right? You speed up upwards, then slow down, and now you're speeding up downwards, and then you speed up upwards, and speed up downwards, and speed up upwards, right? That's what accelerated means, and this incoming wave is doing it, and so the acceleration has a frequency, right? The acceleration is switching, has a frequency that generates, right, electromagnetic radiation. This is the scattered radiation. And this scattered radiation has the same frequency as the incoming, right? This is the wave model prediction. Specifically, it predicts that the scattered radiation is going to be the same frequency as the incoming radiation. But you can see here that the scattered radiation has a sharply defined different frequency than the incoming radiation. And that sharply defined different frequency seems to depend on the scattering angle. This has no scattering angle dependence, right? This wave model prediction. Okay, so how does the particle model work? So I think this is pretty cool. We must use relativity. And the reason that we know this is because, let's think about it in terms of a particle. So I have this little incoming photon particle, right? And it's headed in this way. This is phi equals to 0. And here is a stationary, in a sense, right? A stationary electron in the graphite. And this photon is about to whack into this electron. And so when the collision happens, right? So let's say that this is the collision center. And this is the phi equals to 0 direction. What can happen is there is a new photon. So this is the incoming photon of wavelength lambda. There is a new photon that doesn't have the same wavelength. It has a new wavelength. And we are checking at the scattering angle phi. Now we're being theoretical physicists. We are going to imagine a photon can scatter, and this electron that was stationary there, right, if this photon gets diverted to a new direction with a new wavelength, then what the electron does is it must move away from that scattering center with motion of its own at a different angle in general called theta. So this is the scattering angle of the electron, that's the scattering angle of the photon, and the incoming photon came in from there, but it no longer exists. So in the relativistic, the reason why we need to use relativity is because if you think in terms of the energy, this is an X-ray photon, there is a lot of energy coming in that photon. And this energy, if you could transfer it all to the electron, like you didn't have much of a photon left over, and the energy went into the motion of the electron, you would see that this electron would be moving at a speed real close to the speed of light, is the idea. Because X-ray energies are quite high, especially when you talk about such a low inertia particle like the electron. Okay, so yeah, so we must use relativistic expressions. So this is the energy before the collision, right? So now we're going to do relativistic particle physics. So the energy before the collision, and the energy after the collision is, here's an electron moving, and here's a different energy photon, and you've got angles. But not only are we going to talk about energy, but in order to solve this problem, we have to also think about relativistic momentum. So we'll talk about the momentum before, and we'll talk about the momentum after. And we're going to conserve, right? Right? And we'll see what the conservation of momentum and energy of relativistic particles predicts for us. And it turns out that that conservation predicts this. And that's the big, crazy, awesome thing. Okay, so energy looks like this. So the before case, we're doing relativistic energy. So the before case is we've got this photon. So the thing about photons is, as a particle, massless objects have this relationship between the or actually, let's not go there. So, excuse me. I don't want to introduce the momentum yet. Let's talk about energy purely. So the energy of the photon is, you'll remember this from photoelectric effect, right? So Compton might use this model for the energy of one photon. So this gamma symbol is often reserved for to mean energy of photon. It's not the same gamma factor that you run into in relativity. So I'm going to leave it there. This is the energy of a photon, right? So this is the energy of a photon. But you can also write this as H. I shouldn't have done that. That's too crowded. So it's equal to hc over lambda, because all I did was I used the relationship between wavelength frequency and speed. So I write it as hc over lambda. So that's the energy of a photon. So before, I've got photon energy, but because we're talking about relativity, I've also got electron rest energy. So the energy of the electron is equal to mass of the electron times c squared. So the total energy before is equal to hc over lambda, energy of the photon, plus we have the rest energy of the electron. After the collision, though, I've still got rest energy of the electron, but the relativistic particle energy of the electron is interesting. So the energy of the electron afterwards, it's not just rest energy, because now I have kinetic energy, and the way that gets written down as a relativistic expression is you take the rest energy of the electron and you divide by 1 minus, or the square root of 1 minus the speed of the electron divided by the speed of light squared. So this is the relativistic total energy, not just kinetic energy, but the total energy of the electron. And the energy of our new photon is equal to hc over lambda prime. And so the conservation says that the total energy before and the total energy, which is the combination of these two things afterwards, they have to be equal. That's conservation of energy. So the before is hc over lambda plus m sub e c squared, right, is equal to hc over lambda prime plus mec squared over square root 1 minus v squared over c squared. So if you look at this, first thing you might wonder is, where are the angles, right? It seems like the data is angle dependent, right? The different lambdas are going to be brightest at different angles, is the idea. So where are the angles? And also, if you look at this, I don't know, there's too many unknowns. I've got an unknown speed for the electron, right? That's unknown. And then I have a known lambda, but I have an unknown lambda prime. There's two unknowns, and also some of the important data isn't exhibited here. So it turns out that I can get another couple of equations from thinking about momentum, and momentum, because momentum is a vector, the angles are really important for momentum. So that's the key. I'm going to also, so this is one relationship that's useful, but there's another relationship, it's the momentum. So let me keep this here, right? So theta and phi, so momentum before the collision is all photon momentum. There is no momentum for the electron. And here is what I erased earlier. But so it turns out this is a nice relationship that for massless particles in relativity, there is a relationship between the momentum and the energy of massless particles. So the momentum is, and this is actually, so this is the vector momentum, but it's the magnitude of the vector momentum is the energy of that particle divided by the speed of light, c. So that's how I'm going to understand photons. This is the photon's momentum, because it's a massless particle. Okay, so the incoming, so before the collision happened with the electron, the total momentum was all I hat directed. So I'm going to say that it was equal to the energy of my incoming photon, right, divided by the speed of light, and it's all directed. I'm going to put phi equals to 0 is the I hat direction, so I can put it in unit vectors. And the energy of my photon was h c over lambda. That's the energy of my incoming photon. But now I'm going to divide out a speed of light, right? Because in order to get momentum, I divide the energy by the speed of light for a massless particle, and then I multiply by the right direction. And this looks like just h over lambda. I hat. Right? So afterwards, though, is more complicated. So this is the incoming momentum. That's all there is momentum of a photon. The stationary electron has no relativistic momentum, or it has relativistic momentum equal to 0. So I can add plus a 0, but you know what I'm talking about. So afterwards, though, it's a more complicated story. I've got a photon heading off at angle phi. So that's a mixture of I hat and j hat that's governed by phi, right? So this direction is cosine phi I hat plus sine phi j hat. That's the unit vector that points in the proper direction, or the right direction. And the momentum is related to that lambda prime in the same way that I got up here. So if I multiply this unit vector direction times the correct magnitude of momentum, this is the momentum of the outgoing photon, right? And it's a vector. The outgoing electron, I'm going to write it in terms of v. So in terms of v, so I'm going to add on the electron's momentum. So I've got to go like this. It goes mass of the electron divided by the square root 1 minus v squared over c squared. So I'm writing down the momentum. And then I've got the velocity. The velocity v is the this is the magnitude of the velocity. But the unit vector direction is, so the x component is the cosine of theta. So cosine of theta I hat. But the y component is on the other side of the axis. So I'm going to go like this. I'm going to say minus sine theta j hat, where theta is read positively away. That's kind of sloppy, but I'm going to leave it like this. Yeah, I'll just, so theta is read positively down off the sideways axis, and phi is read positively up from that axis. Anyways, you can now actually, with both energy and momentum conservation, you can get the following relationship, which is really cool. Gives you a prediction. This is a relativistic particle prediction. So the incoming momentum is purely I hat. The outgoing momentum is a mixture of I hat and j hat, but if you conserve momentum, that means the outgoing momentum, the total j hat needs to add up to 0, right? So there's some predictions you can do, some algebra based on the conservation principle gives you an algebra problem, and the result of solving the algebra problem is really cool, and it's so cool I have to look at my notes because I can't remember it. So it looks like this. It says that you can get a prediction that says that lambda prime is equal to the original incoming lambda plus, right? Remember, lambda prime was bigger than lambda, so this is how much bigger it is. It's h over the mass of the electron times c, not squared, but c to the first power, and then you multiply by 1 minus the cosine of phi. So this prediction, this, if you think about it, this is our lambda prime as a function of phi, right? It is also a function of the incoming light beam, but in particular, there's the angle phi, and earlier I was saying that the data says that if you check different angles, at a different angle, you're going to get a certain wavelength that is the brightest, and that predicts that, or this matches the data that Compton got. So the reason that's really cool is this comes from relativistic particle physics, and also, honestly, energy and momentum conservation. Yeah, so the Compton scattering formula, this is the Compton scattering formula. Yeah, it matches Compton's data.